what if we covered the entire visible part of the moon with mirrors? The idea sounds like science fiction, yet let us imagine it as a grand planetary engineering project. The moon's visible surface area is about 19 million square kilometers. If every square meter were covered with mirrors at a cost of $10, the total expense would reach $190 trillion, an investment larger than the global GDP many times over. But suppose humanity managed to achieve it. The moon would become the largest reflector ever built, bouncing sunlight back toward Earth during the night. Would it become a second sun? Not exactly. The sun delivers about 1,360 watts per square meter at Earth's distance, while even a perfectly mirrored moon could reflect only a fraction of that. Still, the effect would be dramatic. Nights would be bathed in a silvery daylight, strong enough to read by, grow plants, and warm the surface. In the first decade after completion, the most immediate change would be the disappearance of true darkness. Cities would no longer need streetlights during full moon phases, and nocturnal animals would struggle to adapt. Owls, bats, and other creatures evolved for darkness would lose their hunting advantage, while diurnal animals might extend their activity into the night. Plants would respond differently. According to studies on photoperiodism, many species rely on cycles of light and dark to regulate flowering. With constant reflected light, crops like wheat and rice could grow faster, while others might suffer from disrupted rhythms. Average nighttime temperatures would rise slightly, perhaps by 0.5 degrees Celsius globally, as the reflected radiation added energy to the Earth system. Winter heating costs would drop. In Northern Europe, where households spend about $1,200 annually on heating, the reduction could be 20 to 30%, saving billions collectively. 50 years later, the climate would show more pronounced changes. The moon's phases would create cycles of brightness and dimness, leading to alternating weeks of strong nocturnal light and relative shadow. Farmers would adapt by creating lunar calendars for planting and harvesting, using the bright phases to accelerate growth. Some regions would benefit enormously. Deserts like the Sahara could bloom under extended illumination, while polar regions would experience milder winters. Factories would evolve too. Traditional coal plants would decline faster, replaced by solar installations designed to capture both direct sunlight and lunar reflection. Glass and mirror industries would dominate, while photovoltaic companies would develop panels tuned to lower intensity reflected light. According to thermodynamic models, the additional energy input could raise global average temperatures by 1 degree Celsius over half a century, a change comparable to moderate anthropogenic warming. After a century, Earth would be transformed. Nights would resemble perpetual twilight. Human physiology might adapt. Larger pupils and altered circadian rhythms would become common. Sleep cycles would shorten, with people resting in multiple phases rather than one long night. Architecture would change too. Buildings would incorporate reflective surfaces to maximize lunar light, and farms would operate continuously. Biodiversity would shift. Some nocturnal species would vanish, replaced by hybrids adapted to semi-light conditions. Coral reefs and migratory birds might suffer from disrupted cycles, but new ecosystems would emerge. Humanity would celebrate the moon as a second source of life, not as powerful as the sun, but sufficient to reshape civilization. The economic balance would also shift. The initial $190 trillion investment would seem enormous, but savings on heating alone would accumulate. If global winter heating costs averaged $2 trillion annually, and lunar reflection reduced them by 30%, humanity would save $600 billion per year. Over a century, that would amount to $60 trillion, not including agricultural gains and reduced energy consumption for lighting. Factories producing solar panels, reflective materials, and adaptive technologies would thrive, while industries dependent on fossil fuels would collapse. The mirrored moon would become a symbol of progress, a planetary infrastructure project rivaling the greatest achievements of history. From a scientific perspective, the project would rely on optics and thermodynamics. The law of reflection, angle of incidence equals angle of reflection, would govern how sunlight bounced toward Earth. The moon's orbit and phases would ensure variability, preventing constant daylight but providing rhythmic cycles of brightness. Studies on albedo show that increasing Earth's reflectivity can cool the planet, but in this case, the added radiation would warm it slightly. The balance between ecological disruption and technological benefit would be delicate. For nature, the loss of darkness would be a minus, threatening species dependent on night. For humanity, the gain of extended light would be a plus, enabling agriculture, reducing energy costs, and accelerating progress. In the end, covering the moon with mirrors would not make it a true second sun, but it would create a new era of twilight civilization. Nights would never be the same. Ecosystems would evolve, and humanity would live under two sources of light, one natural, one engineered. It would be both a triumph of science and a challenge to the balance of life, proving once again that progress always comes with a price.